slides from where I used the last time. Two collaborators that you see the work being discussed here. This is an undergraduate student, a junior student from Fudan University that has an exchange program with UCLA, and he is really totally marvelous in every sense. Doesn't know anything about design, but at the end of 10 weeks, you will see the program he put together for me. Very impressive, and now he's going to do his PhD in Johns Hopkins in the fall. So that's the outline of my talk, some introduction, and I was thinking to illustrate the methodology using meta-heuristic algorithms, what models, well, in fact, can be applied for any models, but for this audience, I think it's not too difficult. I want to use a model that has been discussed, or I think will be discussed by other people, and that's the Hills model, or the 4PL or 5PL logistic models. So that's commonly used. Then I talk about optimization algorithms and demonstration. So what you will see is traditional methods. So the first few slides I'm going to go through very quickly, nothing new, but just a quick review. Key first approach, approximate design. And then what you would want to do is talk about incorporating multiple objectives. We heard about that quite a bit in this talk. And there's some work references there. And I will show you actually it's relatively very easy to incorporate multiple objectives in the design. For two objectives, it's relatively easy, but not a lot of discussion when you want to talk about incorporating 3 or more objectives. In theory, it can be done, but in practice, there are lots of issues how to identify the right objective optimal design that you're looking for. Analytical approach is what we see a lot in the literature, but over the years, I view that as limiting. For a single model, you spend a lot of time and energy deriving the analytic formula. Nobody remembers the formula because it's so complicated. And then if you change a little bit to the model, the whole proof collapses. So people take 4 years just to extend a little bit. But the way to do this, I think, going forward is algorithms. Is effective if you have good algorithms that can generate, in this case, optimal designs for any models, any criteria. Wouldn't that be wonderful if something like that exists? And my conviction is, based on my work 3 or 4 years ago, nature-inspired meta-heuristic algorithm shows exceptional promise, and it's really not designed to find optimal designs. It's a general-purpose optimization algorithm that has been used a lot by people in engineering and computer science. So at the end of this talk, I hope I get a chance to discuss with you quite a bit how to use animal instincts to find simple or complicated optimal designs under complex criteria, multiple objectives. I'll also show for people who really like to see analytic formula. It's very hard to derive because you don't know where the support points are, how many of them. Run one of these algorithms, and it will tell you very quickly where the structure of the optimal design is. And based on that, you can make informed conjecture, and then that will help you arrive at an analytic solution. So I demonstrate one formula for the standardized maximum optimal design. Exact optimal designs, I think there's not a lot of progress. It's very difficult to find, a lot based on number theory, very complicated. But again, using this algorithm, you can also find exact optimal design. The key difference is some of these others they have done, there is no more convex, the criterion. You can verify and be sure you get the right answers. So the idea is I work with a lot of things I can verify whether I have the right answers, and then tackle problems that I don't know. And I would want to tackle problems for which there are some published work in that area. And I want to verify the algorithm give me the same exact optimal designs for people who have calculated, and invariably for very small size problem. And after that, you take it on from there. So supersaturated design is one of the things we tackle, where people produce a lower bound. You know what is that supersaturated design? Small n, big P. So you can only run 10 runs maybe, and then you have 29 factors or whatnot. And how would you exchange the columns appropriately so that it can minimize the average correlation among the columns? So things like that, which is very different setting, you can tell from what we see in optimal designs. So the other things that has been done, but I have to select things. So correlated models, we have verified some of the published work, I think recently by Heuger and Kunert on the Merkeles-Mantel model. So we get those answers, and we would expect that similar things will work for more complicated models. And I can tell you these are good, but if I don't show you some demonstration, we're also busy. I show this to just hopefully encourage you to, this thing seems to work. So I give some demonstration. Last time when I spoke, I did not give demonstration. Last minute, I got cold feet because these are stochastic. You never know how it works out. But I'll try again this time. After last couple of years, I have confidence that you will actually just try a few times and they'll give you what you want to find. So that's a very standard setup. You can read there. And the assumptions are what we typically do in standard optimal design theory. We are not talking about sample size determination problem. Given n, how would you spread out the n observations in the design space? How many observations to allocate there in some optimal way? So for now, let's assume things are simple, things are independent, and we have an information matrix, and the criterion is a function, it's a convex function of the information matrix, so that equivalence theorem may be applied. So models, I was thinking of selecting models and surfing the net. A slide taken from Quintos, and so it's a Hill model, very widely used in all branches of statistics and applied fields. And here's there's a typo, but I didn't change it. There should be a response, and this is the dose, but I leave it there. But there are very different forms. So you might hear of Hill's model, 4PL models, Emacs models, and things like that, but they are reparameterization of one or the other. So it's used very widely in different areas. Depending on the context, you would choose to use a particular form. So here's a little bit more concrete examples. If you chose this form, some people call it a Hill's model. These are some references. I would actually focus a bit on this paper where they had used this model to study, I think, 7 anti-cancer drugs. And they wanted to find optimal design for that problem. So that was inhibitory drugs these people were looking at. And as usual in the nonlinear models, we would like to tease out the meaning of these parameters before we decide what we want to estimate, or some functions of these parameters. So here, something quite standard. Notice that this is a bit more complicated. It's heteroscedastic. There's a lambda sitting there. But in practice, what they did was they assumed lambda is known, but still allowing for heteroscedasticity. So if you plot out the function there, this is the inhibitory drugs, suggesting that if you give the drug at a high dose, then the tumor size will shrink a lot. If you don't do anything, it stays up there, and the slope, that's what n means, and different interpretations of the quantities. So with this in mind, let's see. Suppose we want to estimate some of these quantities, the minimum effective dose, what's the amount of drug I should give so that the tumor shrink by a certain size, delta, or IC50, the dose that will give me a response midway between the two extremes of the doses. And then maybe this objective have varying objectives. Some is more important than the other. You want to find design that can balance these competing objectives. So we work with that model, but work with this form rather than what you see earlier, because some people have suggested that estimates based on this model is more stable than the other parameters. So to find this is a simple exercise in optimal design theory, except to point out that this one here encompasses the 3 or 2 parameter logistic. And then when you raise this to some power, that you have the 5 parametric logistic model, also used quite a lot in ELISA. And we have actually by now generalized this code for 5-parameter logistic. So for estimating all the parameters, D optimality, the prime here denotes the gradient of the mean function, and this is just the transpose. So, and then the ED50, you just use the delta method and try to find a design that minimizes the asymptotic variance. And likewise, for the minimum effective dose, given delta, you want to find a design that minimizes the asymptotic variance of this quantity. So all this is quite standard, and the efficiencies is defined in the way that what you would expect. So the question here is, how do we do a multiple objective optimal design for this? A quick review, if you have two objectives, essentially what you want to do is prioritize which is more important. So these guys are the optimality criterion formulated in terms of a convex function of the information matrix. So this is very important. I want to make sure this is small. And then subjective that I want to do as well as possible for estimating the other thing I want to do. So this thing can be rephrased in terms of efficiency. This problem is very intuitive, but it's hard to solve. So the way to look at it is to look at a compound optimal design approach. And it can be shown that design that minimizes this convex function of a convex function is still convex. This is very easy to find. It's just like single objective criterion. So for each lambda, you will find the optimal design, but it's not clear which lambda you should be using to solve this problem. And the answer actually can be gotten by looking at efficiency plots, and some details are in this function. So here's one example. After you calculate for each lambda, what is the optimal design for so what is a compound optimal design? You evaluate the compound optimal designs in terms of the efficiency under the first and second criterion. They are always competitive, so it looks something like this. So if you want a design with 80% efficiency for the first criterion, that's what you want to make sure you have. You just do this, and then after that, look at the lambda that you should be using, and you should be using lambda about 0.2 in the compound optimality criterion to get the constrained optimal design that you want in the first place. So this design will give you at least 80% efficiency for estimating under the first criterion or attaining your first objective, and subject to that, you do as best as possible for the second objective. Now, when you have 3 or 4 objectives, you can do efficiency plot, but this becomes 3, 4, 5 dimensional, and it's very hard to view what you would do in terms of that. So we have a check-in condition. Just quickly review standard check-in condition because it's convex. We have a check-in condition. When you have 3 objectives, you can do similar things, and in theory, it still works, except that in practice, you just do not know what is the set of lambdas that will give you the design that you want. So some details in the very recent work is in this paper that addresses some of these issues a bit more concrete. A lot of times, many papers just write this thing down and just leave it as that. So in this particular case, if you are interested to find under a given nominal set of values, and you want to estimate these quantities, equally important. So remember, these are standardized criterion. Again, somebody has pointed out it's important to do this. You can verify this is the optimal design. So you do this by equivalence plot, and you see what you want to see. And you can easily extend this idea when you have multiple sets of nominal values, and you're not sure which is the right one. You can average them out, Bayesian, uniform prior. And for this particular case, and for that set of data, there were 7 competing objectives, nominal sets of values. You do that, and that's what you see in the plot here. So all this seems to work fine, but if you want to do this a bit further, and more complicated problems, some of these algorithms may fail. So let's talk about some of the optimization algorithms. They're non-heuristic and heuristic. What you see up there is co-authored by Biederman, who is sitting here. I consider it one of the state-of-the-art algorithms because it was published very recent in JASA. And it works actually, the previous plot were all obtained using this algorithm. I was actually quite impressed. It does seem to work quite well. But of course, there are assumptions built into this model or this algorithm. There are other algorithms that don't need assumptions, and things you might have seen before, genetic algorithm, differential evolution. But what I want to focus on is nature-inspired algorithms, the last couple of algorithms that, in my opinion, and what is said in the literature, not just my opinion, that seems to have outperformed the older generations of algorithms like GA or simulated annealing. And they really don't require any assumption on the problem that you want to solve, regardless of constraints or whether the function is differentiable or not. So what are meta-heuristic algorithms as opposed to the other specific algorithms? They have common characteristics, computational algorithm, iteratively, and then there's some stochastic elements in it, some measure fitness. It makes no assumption, but it doesn't guarantee you will always find the right solutions. But in practice, it always does, as many people would attest to that. So it's all very magical and amazing. So let's talk about nature-inspired. And why nature-inspired? Because they really seem to be taking off like crazy in the last couple of years. So I want to emphasize on PSO, because it's one of the more popular ones, but by far not the most efficient one. As I'll show you, Cuckoo's actually, as somebody alluded to, has outperformed PSO. It's a very dynamic field that I think all of us should pay attention to and try to apply to some of our problems. So this is a conference on theoretical advances of particle swarm optimization. There's no theory behind it. Well, there is, but people haven't quite figured that out. There's pseudo-proof. You impose enough assumptions, it seems that they are coming from, there are two equations that define some of this algorithm. They seem to be coming from Newtonian physics, but they have added a lot of assumptions. So I was impressed in this conference that talks about theory of PSO, why it works so well, and look at the problems here. And I think all these problems are much more difficult than the problem I want to tackle. So that got me really interested to see how it works in my problem. So these two articles I encourage you to read if you are not persuaded by now. There's a computer scientist at Birmingham University. In these two papers, it actually carefully documented the rise in popularity and why it is so widely used in practice. And he also documented that US government patent awards, largely a lot of them are given to people that use this sort of algorithms. So what is GA? Some of these algorithms, well, most people know GA. Differential evolutionary is an advanced version of this. So actually, if you want to use GA, you must well use differential evolution. I'm not going to talk actually a lot about the details of this. They are all over the internet. So particle swarm, I'll say a little bit more because that's what I'm using. So you see how the birds fly in the sky. Why do they fly that way? And what are they doing there? It seems like they're a bit coordinated by some equations. And guess what? So computers, an engineer and a social scientist get together and propose this PSO algorithm. And two very simple equations define how these birds would move. So what are they doing? Imagine the birds are looking for food in the ground. Each has their own perception where the food is. So that's the local optimum, that's where they want to go. But then every bird has their own perception of where the food is. So globally, they share among the flock, and they communicate using these two very simple equations. So what happens is the PG is the global optimum. The PL is what I think is the optimum, and this is where I am. So I want to fly to the global optimum and in the direction of where I think the local optimum is. And then there are other tuning constants, as you expect in all such meta-heuristic algorithms. Some are stochastic, beta 1, beta 2, just to make it random. And this C1, C2 is a constant that how good the birds are at communicating, how perceptive they are. and then inertia, how inertia. So this sort of characterizes the flock. And vi is the velocity for which they fly to the next location, given what they use to fly to the current positions. So this thing may not make a lot of sense, but it's amazing. You can program this in a couple of computer codes, and all these codes are available everywhere. Very easy to find in MATLAB, in ARA, and of course in many, just Google it. There are tons of them around. So the challenge is just take it down and then modify something to do what you want to do. And that's what my students do, and that's what my collaborators do. That's the amazing part of this. What distinguishes from PSO and the rest is like genetic algorithms, all these tuning constants can be a pain. So for PSO, what is amazing is they tell you what constant to use, so that it's not problem dependent. So this probably is one reason why PSO is so successful. In all my work, except for one case, this constant doesn't work, but the rest of it would just work fine if you just stick to this. So you don't have to agonize what to do. GA, you put the wrong tuning constants, you may get garbage. Cuckoo's algorithm is a very recent proposed algorithm that based on cuckoos. It looks nice up there, but this is actually a very lazy bird. If you know cuckoos, the parents, they lay their eggs. They don't want to take care of the eggs. They will just go and look for other nests created by other birds, and their eggs look similar to their eggs. So they would just lay the eggs on other people's nests, and hopefully their mother doesn't know that that's not my egg. So it's parasiter, but based on this, a lot of this doesn't make sense, but so it models after cuckoos, you know, like what's the probability of my egg being discovered by the mother's egg and kick my egg out, and how I should move to the nest is by Levy's flight. So a lot of this may not make a lot of senses, but believe me, it's amazing, it's magical, as some of the engineering professors I spoke to, it's magical and it works. So maybe in a bit of time, let me demonstrate some of this thing. So this is what the undergraduate student have created. And so this is for the Hills model. And there are, as I said, several sets of competing nominal values. Let's pick one of them. And you just specify what's your design region. So here is log, so I chose that. And what's my criterion? It can be D, for instance. I'm looking for approximate design. So I'm looking for D optimality. And I have several things here. Let's try PSO. And then let's say I put 6 birds, and then I say let's try 200 iteration. And I would first of all check how the plot looks like. If not, I would choose a different set of nominal parameters to represent what I want to see. After that, just hit run, and it comes back with these values. And you know that for D optimal design is actually equally weighted, right? So this one's not quite close. So you can look at the equivalence plot. Well, that's not what it is. And you can look at a swarm plot and see how this swarm of 6 birds. So this will actually look like it converges. But remember, this is just a visual plot. That's not definitive. So, but this is more definitive equivalence plot. Well, this one is not the case. So you can either let it run longer, say 600, and see if it works. And this time you see it works, right? And then you will plot this, and you get what you want. And you can actually do the swarm plot, and again convince yourself it does. Now, you could say, I want to find the other types of optimal design. Now remember, this will be singular design, as many of us expect. C optimal design has fewer support points, but this one doesn't care whether your information matrix is regular or not. It will just find the optimal design just as well. So I don't know how much time. Let's go on to compound optimal design, which would also involve. So here I want to look at approximate design. And so it's very easy to compete. So this is the Yao-Ming Biedermann algorithm. And their algorithm, you have to discretize the space. So when you crudely discretize it, it works quite well, but of course the answers are approximate because the support points doesn't capture as well as what you have in the other algorithms. They also require differentiability. So let's say this is compound optimal design, and I need to specify a delta. So let's say delta is 1.2, and I use cuckoos 6 and 600. Let's see, I run this and see what I get. So it tells me this is the criterion. This is CPU times in 2.8 seconds, and those are the function evaluation. Does this work? Let's see. Well, not quite. So what do? You can try a bit of this, maybe increase the iteration of fewer. Oh, so now this is singular something. Let's see. Oh, this, you know why? That compound, so Q1, Q2 are the weights. So let's say I want these weights. This one corresponding to D optimality, this one for IC50. So if I run this, it comes back with something like this. So you can see here, this point probably is not needed, but I want to see how close I am to being optimal. Is almost there, but not quite. And then you just run again, and all this take 2-3 seconds to find the optimal design. Now, if you want to see how well this design does relative to the D efficiency is 93%, this is 69%, and this is about 60%. So all this can be done really quite easily. You look at the swarm plot, it converges or not. This represents the x1, x2, x3. Unfortunately, we can only do 3 dimensions. So this one does suggest, for most practical purposes, it might suffice. Now, there's also an algorithm here for exact, but because nobody knows what the exact optimal design is, it gets some answer, but you can look at this and decide for yourself. You should be allocating 2 points at this location, and then the rest 1 observation there. So finding exact optimal design is really just as easy. The question is, how true is this? We'll wait for somebody else to prove it, and then we can verify it. Okay, so moving back to where I was, further applications. Am I still there? Means. Okay, so this is standardized maximin. And if you know what you want to do, it looks very complicated. I have nonlinear models, and I'm not going to work with locally optimal. People tell me for each parameter, this is the range of values. So I try to find a design that minimizes the worst case, right? Those parameters that give me the largest or the smallest determinant, I want to find a design that maximizes that. So those are notoriously difficult problems. As far as I know, there are no algorithms that you can prove it converges to them. And this was the problem I started when somebody told me to work on PSO. I said, you do it. And actually within a few days, they say, well, we solved it in a couple of seconds. So that really got me interested. So here's one application to Barber's work with Atkinson on inhibition models. So there are many types of inhibition models. Here's just one of them, uncompetitive. So these are the parameters, 3 parameters. And the design space is what you see there. So these things are known. And you want to find the maximin optimal design there, or the standardized maximin. So what they work with is just locally optimal. So we run the algorithms. And very quickly, it tells me there are 3 design points. So the notation is a bit awkward, but we just follow the book. So L just represents the lower bound for the parameter, and L represents the upper bound for the parameters. So all of them are 3 points, and they're all this associated measure that actually is very crucial. These are the subgradient that you need to confirm the optimality of this design. So interestingly, every time the referee will say, well, take this off. You don't need this. Just report the optimal design. But without knowing what this is, you cannot confirm the optimality of this design. So if you focus on this case, it's always equally weighted. And the unknowns are S1 and I3. So these are the extreme points, but you don't know what these 2 values are. Well, PSO gives you the numerical values. But if you want to compute the analytic form, because you really want to see the analytic form, you can see this, but it's not very clear how useful this is, but there you go. You can get an analytic form with the help of PSO. PKPD. So this is the paper that 2011, when I was here at this conference, up in the library, I saw this article that really excited me. It says a novel global search algorithm for nonlinear mixed effects models using PSO, and it's published in the Journal of Pharmacokinetics and Pharmacodynamics. And up here, you see, it's talk about no Nomen. Have you read this? This is, so I did contact this author and have some follow-up work, which I'll show you in a bit. This is what with us, we tend to really work in a very close area of algorithms. And just like PSO, it's not new even in statistics. If you search 1996, there was an article published in Computational Statistics and Data Analysis, and talk about how PSO can be used for clustering purposes. But I, like myself, I ignored it and didn't pay much attention. So you may be interested to just read this thing up, because it references your no-name work as well. So one of the latest work I did was, well, how can we use this for adaptive? And phase 2 trial Simon two-stage design. I hope many would remember what that is. It's a one-arm trial, and you want to know how efficacious the treatment is. So tell me how many subjects I should recruit in the first stage, and then if I see X number of responders, what will I do next? I want to test in the second stage whether the hypothesis is this, and maybe if I have a lot more responders, then I would test at the second stage a hypothesized value for proportion of responders at a higher rate. So this is what these two people did. And then, well, we just said, well, let's extend this to 3 target responses instead of 2. And what my co-author said was, he's at Wayne State University now, and he said that if you do a greedy search, this thing will not even work after letting the computer run for 30 days. And this paper by Ling and Shi, they did make a comment that for 2 target responses, they can do it, but anything more than that, it would be quite an impossible task computationally. So I thought that was a good problem. I said, you can figure out how you do that. And so basically, in our problem, what you see is something like this, recruit so many subjects, and depending on the responders in the first stage, then you would, in the second stage, you want to test a hypothesis and power it appropriately at a higher and higher proportion response rate. So this is just an extension of that, but it turns out that for some of these standard criterion, you want to minimize the sample size or the expected sample size under different hypotheses, and also at the same time subject to minimizing the total number of sample sizes.
Do you mind making full screen?
Yes, you can't see anything.
It's not full screen? Oh, sorry. Yeah. It may not help, but this work actually was just sent to me just this week. I was working on it. And here's a table that you probably cannot see too. But the point is, so this is standard Simon design. This is the two target response. So you see all these parameters here. You have to tell me what is N1, how many subjects to recruit in the first stage, how many responders I should see, and if this responders falls within certain ranges, I'm going to target at the second stage what hypothesis I want to test. So the greedy search, which is what is the current strategy for doing this sort of thing, is actually brute force, right? For each, all these parameters, you vary their values and see whether you get what you want. So even for PSO, what is very interesting here is you can have 7,000 more times. Even for this problem, there are 10 parameters to optimize. Depending what type of PSO you use. Remember I said hybrid, and actually a lot more things going on. Topology, what kind of topology you use, how do you measure closeness. So there's a lot of other details, but even PSO, it can vary. Using a standard PSO, it will take 1,500 minutes for you to find a solution, versus if you are smart enough, you can find it in 6 minutes. So very interesting things that we do not get trained in this area, how to improvise and improve algorithms, hybridize them to take advantage of different algorithm strengths. Closing remarks, there are many other things besides that, so I don't want you to think about PSO, but PSO, I would contend, is still one of the most popular things you see in the internet. How medical schools use PSO to simulate flesh-eating bacteria, or Hollywood studio using it to simulate thousands of soldiers fighting. So they're used everywhere, and go to YouTube, there are 16,000 hits at least. So this Firefly that I haven't actually had a chance to look at, but what I know is there's people mention that cuckoos outperform PSO. It used to be differential evolutionary, which is more for discrete optimization, is competitive with PSO. But Firefly, well, I don't know much about until I received from AT&T, which is one of the biggest telephone company in America. So I asked me to sign up for this, and I saw, oh, Firefly technology. And right away I think, oh, are they using Firefly algorithms? So I think in practice, a lot of these things are actually used in practice. So that tells me there are lots of interesting applications for this. If you're interested in meta-heuristic algorithm, this website gives you a chronology, very historical development, and with codes and applications, tutorials. You can visit it. Another one is here. MATLAB, I have some codes there, but I was just informed this site may be just taken down because of security threats. So this may not work for a while. But otherwise, get this book, $16. It's a book that documents all these advances. He wrote the book in 2008, and before the end of 2010, he is so compelled to come up with the second edition because he said the field is evolving so rapidly. Maybe some other remarks, not to talk about non-heuristic algorithms. There are other types. And this is an engineer who got in touch with me and want to apply his way of doing things to solve some of the problems he sees. And so those are semi-infinite and semi-definite programming. And I vaguely remember reading this, the cutting plane algorithms, 1966. I saw that, but again, I did not pay much attention. So I work a little bit in this area, and my experience is, yes, they work. They give you numerical answers, not analytic solutions. And as I think Harman pointed out, many of these methods can solve problems with hundreds of parameters. So in the design problem, except that they cannot write down. So for engineers, that's very good and just fine. But I think we have to get used to solving real problems where you have numerical answers very quickly. The downside to using this, I think all this thing looks good, but you really need to be more trained in this area to use this. So what you use is sometimes you find that this thing doesn't work, and you can actually solve problems that I cannot solve using the conventional approach. So for this thing, if it doesn't work, that just simply means you did not use the right solver. So there are websites that they go to, tomlab.com and other stuff that we are not usually aware of. And you just match the right solver, and sometimes you have to pay for it. I guess the more complicated problems, you have to pay to get the right software. You put them together, and they could actually generate equivalence plot and all those things. So think about this as well, but my preference is still meta-heuristic because you can just modify the algorithms and do something else. So here are some references that I have for you about PSO applications to design, specifically in design. There is not too much actually application of PSO outside design. I see quite a bit in bioinformatics for clustering. So I think there's a lot of applications for PSO in mainstream statistics as well. So I think my time is up, and so thank you for your attention.
Time for a few comments, questions?
Yes, thank you very much. It's very exciting because we do have very complex problems to solve. My question is, in the PSO algorithm, how often you need to compute the criteria? Because for us, for instance, it could take like 6 minutes just to compute the criteria for one design. So is it
to compare? So you have a
just the criteria. So how is it very?
No, of course it depends on the complexity of the problems.
Yeah.
So for engineering professor that I talked to at UCLA, he has a PSO lab, and he has all these postdocs and students, and it's sponsored largely by NASA, and I forget what else, that his job, so I asked him, what kind of optimal design you do? I do design, but I don't do optimal design. Why you want to find the best? There's no such thing as the best. So what I do is I have a contract with NASA to improve satellite communication. They say, I want to have this communication system that meet all these 19 or 22 criteria. So I just use PSO, and then you run, and after you miss everything, my job is done. So we're not looking for optimal design. They tell us what they want, and we deliver specific to that. So in his case, he said, oh no, one iteration can take days and days. But of course, it's very problem specific. I'm sure his is much more complicated. But I have other things which I did not have time to talk. How to compare algorithms is another big issue. And in many cases, for publication-wise, referral, how does this compare with other algorithms? In many senses, Xiao Liming recently had an article that said, all this is nonsense because the algorithms are motivated in so different ways, and one iteration is so different from another iteration. So, and some problems have do transformation inside. Like, even you talk about PSO, there's at least 10, 20 versions of improvement now. So when you say PSO, which version? So a lot of things that goes into that, but I would imagine it clearly depends on the complexity of the problem. But I would really try to investigate it. And students are very good at doing these things and think better than older people.
And postdocs using that.
Anybody else?
Very interested in the modern algorithms. I had an activity some years ago, almost 20 years now, I guess, looking at genetic algorithms when they first came out. And it was a bit scary because the things that people say about them are very strange. I mean, there's a theorem that's meant to prove that this is why they work, and you look at it as a mathematician and say, well, it's not even a theorem, and it doesn't prove anything. But I think the thing that I saw happening was that people were using them very enthusiastically, and people who didn't normally optimize anything in their processes, and weren't inclined to go to a math department and say, find me a numerical analyst who can tell me how to make this function have a higher value. They had fun playing with these algorithms, and they wrote lots of papers about improving their production processes and so on. And this seems like a modern version of that, where computers are bigger and faster, and the objective is very different from what you're sort of, I think, trained to think about as a conventional mathematician. Like, what's the most efficient way to do it? Have we found the optimum? Your experience with the guy in UCLA was, no, you're given a problem, you throw resources at it, eventually you say, I've got a solution that's as good as what you want. It's a very different mindset.
It's a very, very different mindset. In fact, another engineering professor at UCLA, he had 26 million of funding from NIH. And when I finally get to meet with him, why are you talking about these doses, responses, herpes viruses? I mean, you seem to be from School of Medicine. And he was saying, well, it took me 10 years to convince NIH I'm deserving of funding, because it's always, in his word, the damn biologists, toxicologists, and all these theoretical people who say, you cannot do this until you understand the whole biological process. And my response has always been, wait until you die, you still wouldn't understand those things. I have a job to do just like a doctor. I need to treat patients right now, and I think I should be doing what I think is best in the current world. So engineers have to deliver the task. Very different mindset. So about this thing, the thing is, first of all, nobody knows the true answer when you get to exact optimal design, things like that. Nobody knows the right answer. But I can produce an answer, and for the more theoretical people, they do not have an answer. So that's, I think, the mindset. Yes, it's a different type of mindset. But for what I do, I start off with convexity. Everything is just confirmed. And even for exact design, for whatever work I see published in the literature, I just verify it gives me the right thing. So of course, there's a leap of faith to say, well, why wouldn't it apply to finding design that minimize bias, mean square error, and things like that? But I think it holds really exceptional promise for increasingly difficult problems. And the idea of you have to prove everything for real problems like fMRI design experiments, that if you know the details, what we have typically trained to do is put assumptions and solve the problem. But this thing has a different approach to it.
But you can tell if you've done better, right? You can.
Yes, that's right, criterion value. Yeah, so the way this thing works is maybe 10 years later, somebody publish a paper. I have a better criterion value than you are, therefore yours is not good, and mine is a better algorithm.
I think for the sake of time, I think we're going to stop it here and go to the coffee break, because otherwise no time left for coffee. Let's thank everyone.
Thank you.